let's imagine you are building a drawing application. You know your app will support circles, rectangles, maybe triangles later. But here is the problem, every shape must be able to draw itself. Now ask yourself, how do I force every shape to implement a draw function? That's basically where a pure virtual function and abstract classes enter the story. Pure virtual function is a special kind of virtual function that has no definition in the base class. So it only provides a declaration of a function at the base class level, and pure virtual function is specified by placing equals to 0 sign in its declaration. Like you can see in this class, we have declared one pure virtual function named getVolume. Let's say we create a base class shape and imagine it has a draw function, but wait, does a generic shape really know how to draw itself? So the answer is no. Shape could be a circle, shape could be a rectangle, so each one draws differently. So giving a default implementation doesn't make sense. We do not want a meaningless default version or someone forgetting to implement draw function. So what do? We tell C++, I do not want to define this function here, but I want all drive classes to define it. So this is done or ensured using that equals to 0 sign, that is with the help of pure virtual function. So you can see in this example a shape class, and we have defined a pure virtual function named draw. So virtual means to ensure that it enables runtime polymorphism. Equals to 0 signs makes it a pure virtual function. So now shape becomes an abstract class. So abstract class is a class that contains at least one pure virtual function. And there are some important rules. You cannot create object of a abstract class. You can create pointer or reference to it, and it must be inherited, and drive classes must implement a pure virtual function. So these are some rules associated with your abstract class. Now we create real shapes. So a circle class inherits from shape and it draws according to its behavior. Notice something important. If we forget to implement draw inside a circle, then the compiler will throw an error because we promised to implement it. That's the power of pure virtual functions. Now look at the main function. If we try to create a shape object S, so as this is a abstract class, so we cannot create an instance of it. We can only create pointers or reference to it. So this will throw an error. Next we create S1 pointer to a shape class. We are saying I don't care which shape it is, treat it as a shape. This is called upcasting. Now here's the magic. Even though the pointer type is shape static, that is of shape, the function called is of circle, that is the draw function will be the version that is placed in the circle class. That is because of virtual function. So this is called runtime polymorphism, late binding, that is the decision depends at the runtime. Now let's see what is interface in C++. So imagine again you are building a powerful graphics engine, for example. So you know one thing for sure, that every shape in your system must draw itself, calculate its area. But here's a twist, you do not know yet what shapes will exist in future. That is maybe circle, rectangle, triangle, or maybe even hexagon someday. So how do you design something flexible? That is where the interfaces in C++ comes in. So the core idea is that an interface defines what must be done, but not how it should be done. Think of it like a contract. So it says if you want to be a shape, you must know how to draw and calculate area, but it doesn't tell you how to implement those functions. So here's an example. Let's break this down stepwise and discuss. So we have a shape, we have a class named iShape with some pure virtual functions and a destructor. So equals to 0 sign basically makes them pure virtual function. That means no implementation here. Drive classes must implement them, and this makes iShape as an abstract class. Then virtual destructor. So why virtual? Because when deleting objects using base class pointer like delete S1, we want the correct derived destructor to be run. So this is good practice in polymorphic. base classes. Next we have a drive class circle that basically inherits from the I-shape class. The constructor initializes radius, so if we write circle C 5.0, then this will put the radius as 5.0. Now notice this is the draw function. So this is circle's own version of drawing. So again, the area function, the formula used is pi r square. So the circle calculates its area accordingly. Then we have a rectangle class with its constructor, parameterized constructor, the draw function, overridden draw function, and overridden area function. Now a rectangle area is calculated with a different formula, that is width into height. So it is accordingly specialized behavior embedded into the draw function and area calculation function of the rectangle class. Now let's see the magic. So in the main function we have created two pointers, S1 pointing to referring to a circle class and S2 for rectangle. So we are using a base class pointer. So again, this is called upcasting. We treat circle and rectangle as a generic I shape. Now when we write a statement like call of draw function using S1 pointer, so even though the pointer type is I shape, at runtime it is decided to call the draw function of a circle class. So it prints a message drawing a circle. So this is runtime polymorphism. So even though both the pointers are of I shape, different functions are executed because of virtual functions, the vtable mechanisms, and the runtime polymorphism. So the big concept is interface, that is a common behavior, that is all shapes can draw, all shapes can calculate area, but internally circle uses pi r square and rectangle uses width into height formula. So same interface but different implementations. So think it of as a remote control. Every device must implement power on, power off, but how TV powers on is different from the air conditioner maybe. So remote defines what must exist, but the device decides how it works. So that is exactly what interfaces do. So this enforces consistency, make the system scalable, and it allows adding new shapes very easily. Now let's discuss another important concept, that is virtual inheritance and the diamond problem that we slightly briefly discussed at the start of this session. So imagine you are building a class hierarchy. You start with a simple, you create a big base class, maybe class A. So far everything is fine. Now you create two classes, class B and class C, inherited directly from class A. So both B and C inherit from A. Still okay. But then you create a class D, like D inheriting from B and C. So the chaos begins. So let's visualize this inheritance structure. So this creates a diamond. So this is called a diamond problem. Let's see why. Because D gets two copies of A, one through class B and one through class C. So inside the class D, so in the class D you have a show function that basically prints a value. So when you create an object of D and then write obj.show, so the compiler gets confused. It asks you which value, either it is a B's copy of A or class C's copy of A, because D contains both, as it is inheriting from the both of these classes. So internally memory looks like having D having both the versions, so compiler can get confused. It sees two separate A objects. So that's why it is ambiguous. As a temporary fix, you could write a scope resolution operator, that is C or B of value or C of value, but that doesn't solve the real problem. You still have duplicate A objects. So the real solution is virtual inheritance. Now let's rewrite the B and C like this. So while inheriting, you insert a keyword virtual. So class B colon virtual public A, again class C colon virtual public A. So that single word virtual changes everything. It tells the compiler if multiple classes inherit from A, share one common instance of A. So now memory structure becomes easy to comprehend. Internally, D has only one A shared instance. Now let's revisit the example. We have created B and C virtually. So even though both inherit A, they do not create separate A objects. Now the value variable is not ambiguous, and if you see inside the class D, because there is only one A associated with D. So the constructor order is very important concept. When you create an object D obj, number one, the virtual base A class A is constructed first. A constructed message is printed. Then B constructor runs and B constructed message get displayed. And then C constructor runs and C constructed message is displayed. And finally the D constructor runs and D constructed message is displayed on the screen. So why is A constructed first? Because virtual base classes are constructed by the most derived class. Even though B and C inherit A, they do not control its construction anymore. So D is responsible.